Hi everybody, what we're going to do in this video is talk about two-way between subjects analysis. I've already posted a two-way repeated measures analysis that I went over in class, but this is an example of two-way between subjects. I think you'll mostly have to ignore the dog noise in the background because she's very hyper and is trying to get my attention. So, let's get started. So one quick thing about between subjects is that you still have to use Levenes test, just like a one-way ANOVA. So we're going to get Levenes for homogeneity. And we'll get an analysis that looks at just variances by condition. So unlike Mockley's, where you sort of get it for each IV, in this case we're going to get it one big condition-based IV. Especially good because we're interested in the interaction. Normally, otherwise, you wouldn't be doing a factorial design. We're going to get main effects, which is where we interpret each IV on its own, ignoring the effects of the other IV, or basically averaging across the other IV. And then we'll look at the interaction. So if you have a two-way between subjects analysis, you'll actually get 3 F tests, one for each of the two IVs and one for the interaction. Next thing I did was just sort of make a little chart of like how you might analyze these. So if there are only 2 levels in an analysis and the main effect of the ANOVA is significant, there's no follow-up test to run. You just interpret the means because 2 levels means it's pairwise, and that's the same thing as running a t-test for ANOVA. It's just t squared for F. So we don't want to run a second test, run the test again, essentially. So we don't want to repeat ourselves. If there are more than 2 levels and the main effects are significant, you have to run some sort of post hoc test. Usually the test is independent t, running things by pair by pair, sort of the Noah's Ark example. There are other types of tests like contrast, pair contrasts, and plane comparisons, but mostly I'm just talking about doing everything pairwise. I'm teaching a Bonferroni correction because it's definitely the easiest thing to run in R. There are other types of corrections, and if you watch my ANOVA video, I talk a little bit about Tukey. And then if the interaction is significant, we have to do something. So we're going to split up one of the IVs and analyze the other IV as an independent T. So we're going to break down the interaction, which is 2 pieces, into one piece and analyze each of those little pieces separately. So when you're running ANOVAs, the more IVs you have, the more you have to break things down. So if you have a 3-way ANOVA and that interaction is significant, you look at the 2-way interactions. And if those are significant, you look at the 1-way effects. So we're sort of breaking it down piece by piece. Okay. Often if the interaction is significant, people will ignore the main effects because that reduces type 1 error because you're running less tests. And if you're interested in the interaction, why only look at one of the variables anyway? So for this particular example, it's not necessarily the best example, but it'll run, so that's good. We have 2 years worth of athletic spending for different sports, so there are differences in these sports across years and spending. This is by transaction. This is a data set I found online and modified to be about athletes. So the file is the BN2 data set, which if you are not in my class is on our website, Stats Tools, or it will be next week. So our first IV is years and it has 2 levels. So if this main effect is significant, we wouldn't analyze it. We would just look at the means. And then type of sport has 3 levels, or 4 levels: basketball, baseball, volleyball, football, and soccer. 1, 2, 3, 4, 5, I can't count. And so if that's significant, we'd have to run a post hoc effect on the main effects, but really we're interested in the interaction. DV is how much people spent on each individual sport. So we're going to talk about power. So I love G-power. And so for this type of design, what we're going to do is pick an F test under test family here. And then for between subjects with interactions, we're going to go ANOVA, special, main effects, and interactions. If we have an estimated effect size, now in psych we don't use F very often, so I always like to hit determine and then go direct and enter an eta squared that I'm familiar with. So let me see what my notes I did here. I did a medium effect size, so I'm going to go 0.09. Calculate and transfer to main, we'll transfer it over here to F. Now that is a little bit bigger than the F estimated medium effect size of 0.25. because some people disagree on eta, so I could also go 0.06, which is the more traditional version, but I like 0.09 because it matches R. Oops, calculate. Alpha is 0.05. We use power as 0.8 because we like a type 2 error to be 0.2. That's beta. Numerator df is going to be, for the main effects, levels minus 1. For interactions, it's levels minus 1 times levels minus 1. And that's just how degrees of freedom is calculated for ANOVA. So for this particular example, it's 2 minus 1 times 5 minus 1, so it's 4. And the number of groups, since we're interested in the interaction, is the number of conditions, so it's 10. So 2 for the years times 5 for the sports, and that's 10. So it says we need about 126 people for a medium effect size with a 2x5 design. Right? That's not too bad, people-wise. And so I would split that between my groups because this is all between subjects. All right, so I'm going to run through and I'm going to type just a little bit of this, and then some of this I've kind of cheated. I have it typed out, so you can see that I can cut and paste some code that we would use over and over again. Let me make this a little bigger. So first thing you want to do, I like to set my working directory where I have these files so that I don't have to type this big, huge, long thing, because I like folders and folders. But the next thing you want to do is import the data. Okay. So I'm going to call this master for my master data set that I'm starting with. It's read.csv, right? And then the data name. So the data name is bn ANOVA. Oops, come on. .csv. I think it's bn2 actually. Yeah. And so that imported the data set. And so year and type look like they came in. Year came in as an integer, so I probably want to fix that. Type came in as a factor. That looks pretty good. Money came in as a numeric. So we're doing pretty good so far. But if you're going to use import dataset from text file and find the file, it's going to spit out. So let's say I call it master here. I clicked import. It's going to spit out all this code down here. Be sure you're copying that and putting it in your scripts so you at least have that saved. I've broken that into 2 steps by having a working directory and then the name of the file, because I'm more likely to move the file than I am to rename it. And that just keeps me from having to change a bunch of lines of code or forgetting to import the dataset. Alright, so the first thing we're going to do is check for accuracy. We're going to use the summary function for that. So I'm just going to run summary of a master data set. And looking here, I really got to factor year because it is a factored variable and we wanted to treat that as a factored variable and not an integer. My type of sport looks pretty good here and they're all proper case, so that'll be nice for later so I won't have to fix them. And the money here looks pretty good because none of it is negative. So I'm just looking for typos or issues or reverse scoring. But let's fix that factoring. So first thing I'm going to do is factor the year variable. So I'm just going to override it by using the factor command. On my levels here, I just want it to be 2007, 2008. Okay. Whenever you do levels, levels has to be what's in the data set. So I could make a little table of what's in the data set. And it's clearly 2007 and 2008. Now you can also relabel them if you'd like, but I don't need to in this example. They are the labels I want them to be, I just want it to be factored. Now if I run that table again, it's going to look the same, but see over here it says factor with 2 levels. So now it's factored variable and not an integer. So we fixed all that. When I ran the summary function, so here's the results of that. Now if I run summary again, you'll see that it's going to look a little different because this is a factored variable, so it doesn't give me mins and maxes anymore for year. And I can tell I don't have any missing data. So, nothing to worry about for missing. Now, with outliers, one of the things I've been teaching is using Mahalanobis distance, which accounts for the fact that each person is their own person and looks at the pattern of scores for each person. The issue with that is that Mahalanobis distance requires at least 2 columns because it looks at the covariance matrix, which is the unstandardized correlation matrix. So it looks at the correlations between people being their own people. And we only have one thing to screen, one DV. So with univariate with univariate ANOVA, so one way, two way, three way, for between subjects, we really only ever have one column. So we can't use Mahalanobis. So instead we're going to use Z-scores. The rule for Z-scores is an absolute value of 3. That's p less than 0.001, which follows our big important rule from the data screening notes. So what we're going to do is just create a Z-score column of the DV. So I'm going to use the scale function. Okay. What that does is it just creates a Z-score of all of them. But then I want to check. Let's check and see if we have any outliers. So I can use summary, but I'm going to use the ABS function. So ABS of your Z-score here is the absolute value. So let me show you. So if I run Z-score here, I get a whole like crap ton of numbers, and it's like, don't do that. If I run absolute value of the Z-score, I just get all positive numbers. This is giving this to me in scientific notation for fun. So if I run a summary of the absolute value, I get at least a prettier picture, right? So I do at least have some outliers. Look at those max values. It's over 3. But the reason why you want to do absolute value is so that you can check the lower and upper Z-scores. So these can be positive and negative at the same time. So that'll allow you to capture scores that are both too low from the mean and too high from the mean at the same time. Okay. So if I do my summary here, how many Z-scores are less than 3? That's a good thing. We want them to be less than 3. So here are all our normal scores. And anything greater than 3 shows up as a false. So I have 223 outliers, which seems like a lot until you realize I have 8,000 lines of this data set. So I have some outlier scores that are either too low or too high. And now in this data set, they're actually real data, well, real fake data. So I might not consider eliminating them because they are real transactions. You just make sure there's not a typo or something. But for this example, we're going to exclude them just so you can see how that works for your own data. So we're going to make a no outliers data set where we exclude based on our Z-score column. So what we're going to do is subset the master data set by using this rule here. So that's why I did my summary the way I did, was so that I can use that rule. Keep anybody whose absolute value of their Z-score is less than 3. I know the Z-score column isn't actually attached to my data set, but that's okay because it's got the same number of rows. This will have a small fit if you don't have the same number of rows or numbers of things. So 18,260, 18,260 here. Okay. So it should have eliminated 223 people. So 18,260 to 1837. That looks good. Additivity is not necessary, so we're getting into assumptions now because we only have one variable, one continuous variable, so there's nothing to correlate it with. And you do want it to be related to the IVs, that's the point. So we're going to not try and correlate this with our categorical variables. And we're going to set up the rest of our assumption tests here. So this is sort of an assumption setup. So I'm going to make myself a random variable using the r chi-square function. R chi-square requires the number of rows, or an n value, so I'm going to put in my data set. And then 7 because I like it and it works. So this is going to create me a random variable to compare my data set to. I'm going to then use use my data set to predict my random variable. So I've got random is y is predicted by the data, so the entire data set. So this will make sure that the combinations of conditions are not weird. And I'm predicting my random variable, so then my scatter plots and things should look random. And that'll help us just screen the data. So data equals no out. So one of the big things is here, make sure you use the last data set you created here. So I created this fake regression, so I've called it fake so that you know you're not using this for real analysis. And in my, what I want to pull out of that is the standardized residuals, or the studentized residuals, either way. So that's the R student function. And the fitted scores. So the prediction of the DV of the random variable with my data, which should be random because we're predicting a random variable. And that's fitted values. So we're going to scale them to z-score them. Okay, and we're going to use our fitted values. The scaling, all that does is z-score it, so that gives us a nice a 0 to be able to interpret these a little easier. Now that we've set those up, let's do normality. So I should do a histogram of the standardized residuals, and that should be normally distributed. And you'll see that most of the data is between 2 and 2, which is good. It's centered over 0, which is good. It does have a tail, so there is a little bit of skew even after the elimination of outliers. But since most of the data is between 2 and 2, I think it's okay. And normality-wise, if you have at least 30 people, the central limit theorem kicks in and you're okay. We have 18,000 lines, so we should be good. Okay. ANOVA is very robust to non-normality, but I would say that little tail isn't going to cause us too many problems. Let's check linearity with the QQ norm function of our standardized residuals. But to aid interpretation, I'm going to add a line at 0, 1. And this will also match SPSS if you're familiar with looking at those plots. It's a PP plot. This is not so good. Between 2 and 2, it's mostly on the line, which is generally where you want it to fall, because think about this as z-scores, and you know, it's hard to predict the tail. So everything past this 2 out here and past this 2 out here is difficult to predict because there just aren't as many people there. But this is kind of problematic. This is pretty much nonlinear because if you can sit in it, it's not linear. Okay. Now, putting a linear line on nonlinear data reduces power, so you're less likely to find a significant effect. And so you should consider trying some of the RFIT functions, which is a package that'll do nonlinear trends, or there are a couple of other ones in LME, but that does mixed models. And so there are ways to estimate nonlinear designs. But the purpose of this is to show you between subjects ANOVA, so I'm going to keep going. But I would stop and normally consider something else. Maybe like a Kruskal-Wallis, Friedman's test, one of those types of things. Mann-Whitney. So there's a couple of different options if the data is nonlinear. Here, I put them in here. Friedman's, Mann-Whitney, and Kruskal-Wallis are kind of the big ones. So let's do homogeneity now. So we're going to make a plot of our fitted scores by our standardized residuals. Both of those are z-scored. So it's going to create us a kind of scary looking plot in this small window over here. But again, to aid interpretation, I'm going to add a line at 0, 0 and a vertical line, v equals 0, to just make it easier for me to read. And then when we zoom, you can tell this is very not homogeneic, so it's heterogeneic. You want the data to be evenly spread around 0, so I added those lines, and it most certainly isn't. On this axis here, it runs from 1 to -3, from 2 to 6, very much not homogeneous. We'll take a good look at Levenes' test to see if that test also indicates heterogeneity. Now, if you aren't sure about something or it seems close, you can always try rerunning your random effects. Oops, wrong button. Try running these plots again. Give it a minute, it's a little slow. And I would say this is still bad. So every once in a while you'll get it is a random prediction, you'll get a really random plot. This looks a little better on this axis now, but it's still pretty clear that it's bad. This looks like a forest, so that's not good. Now, we'll get Levenes' test when we use Easy ANOVA, so I'm going to look at that first after I get my Easy ANOVA output. Now, when I'm running the ANOVA, first thing, for Easy ANOVA at least, I have to have a participant number, which I do not have at the moment. So let me add that. Okay. So I'm going to add this to my no out data set because that's the one I'm using. I'm going to get it a new name. And so I'm going to say, I just want to number them. So 1 to the maximum number of rows. So in row, no out. And what that does is it adds just a participant number on the end. Which is good because now I need to do that to use Easy ANOVA. So you'll want to load the Easy library. And we're going to run a all between subjects design. Okay. So what I want to do is do Easy ANOVA equal, open parentheses. And what you do is data equals, and put it in your data set. So I got no out going. DV equals, so my DV is money. Within subject's ID, this is participant number. Between, because we're using between, you're going to use dot, open parentheses, and list both variables. So I've got type and money. Oh, you can't see me typing. Let's try again. All right. Thought R was going to have a moment there. And then type equals 3. You want to do type equals 3, it's going to be type 3 sum of squares, which is going to match your major statistical packages, SPSS, SAS, Excel, JASP, PSPP, a bunch of different things. So type 3 is the most common, but if you're interested in the differences between 1, 2, and 3 in R, there's a really great blog. Just Google type sum of squares in R. You can read all about it. But type 3 is usually recommended, especially with interactions, if you don't have an order to the effects that you're interested in. All right, so let's run that. It does take a moment to run. Mostly because it's a huge ANOVA. There it goes. And my computer is going slow today. One or more cells is missing data. What did I do wrong? Let's see here. So I've got data equals data within subjects between DV type. Data, DV, type. Oh, I made my DV and my IV the same. Whoops. That's no good. Let's try that again. That should run much faster. Well, I say that, but now it's not. There we go. So the output that you're going to get is I will get my ANOVA pieces here. So one at a time. And then Levenes test. So I'm most interested in looking at Levenes first. It's got crazy degrees of freedom, but here's my p-value. It is definitely less than 0.001 because that's the big important rule that we're looking for here. And so the homogeneity chart and Levenes definitely agree. Now, with such a huge design, Levenes is oversensitive to the number of participants. So in the same sense that you get extra power for having more people, you also get extra power for finding a significant difference in variances. So you may want to be wary of Levenes. And in this particular case, there's not really a whole lot I can do unless I want to switch to a non-parametric design. And since linearity was bad, I probably would have if this were a real analysis. It said we will forge ahead, but with the warning that you probably should make sure you understand your assumptions. Next thing I did was I turned off scientific notation so you could see it a little better. And so what we're interested in really is, are these effects significant? And so I have the stars here next to the first two, and so they are. So year is significant and type. And what that means is that there's a difference in years and a difference in type, but there's no interaction. I'm going to show you how to run an interaction in this analysis, but with the warning that I would not normally calculate the interaction because it's not significant. So for main effects, for year, what I'm going to do is run tapply. And you run that. It's DV first, it's money. And then IV that you're interested in. I'm going to use the list function. You'll see here why in a second. Year first, and let's look at the means. So the means for year were significant. So I can see here it's significant. And that has the largest effect size. So GES is a type of eta type effect size. It's not quite eta squared, but it's very similar. And so the 2007, they spent more money than 2008. Cool. So they're using less money per transaction. Now I could also look at the means for my sport. Sport. Oh, gracious. It's always DV first, comma, type should have gone here. And so these are significantly different, but it doesn't tell me where because this is still ANOVA. So I would need to do something here to be able to understand how they're different by sport. And the simplest solution is to use pairwise t.test and analyze that main effect. And so what we're going to do, let me scroll down here. This just explains how you interpret everything. And this is a between subjects ANOVA, so we want to use independent T. And it's DV, IV, and a couple of other things that we want to add. So let's start typing that. So it's DV, so I got no out, mine, if I can get this correct, money. And then IV, we're going to use type for this one. Go away. Paired equals false. Now that's the default, but I'm going to go ahead and type it just to make sure I know I'm running independent T. var.equal equals true, but in this case, since Levenes was significant, we probably should actually make that false. But it does do false as a default, so make sure you understand, like one time it's going to run Welch's test for false. Another one's going to run traditional independent T for true, so make sure you understand which output you're looking at, because Welch's will look different for you. And then the important part, p.adjust method, as Bonferroni. Okay, there are a couple of other ones, home, and some other tests. Bonferroni is the most familiar to people. There are some arguments on which one's the best, but here's how you run Bonferroni, and it will adjust for all of our pairwise combinations. So see how it says pairwise comparisons using pooled SD. If I change this to false here, it will change to, oh, I thought it would run Welch's test. It might run Welch's test in the background and just not tell you that it's running Welch's. Okay. All right, so here all of my p-values are in scientific notation, but they're all significant. So even after correction, all of the means are significantly different from all of the other means. And so what that means is that basketball is the lowest spending per transaction, then baseball, then volleyball, then soccer, then football. So we could rank the sports by how much they're spending. All right. This is a comment on how you would run a interaction, even though you shouldn't in this particular case. But what we want to do is we have 10 conditions, and we want to figure out how to compare them. If I compare down here, it's going to be 5 comparisons. So baseball by year, basketball by year, blah, blah, blah. Or I could compare across. So in 2007, what was the rank order of sports? In 2008, what was the rank order of sports? If I didn't have a specific hypothesis, I would tell you to compare going down here. Because that would be 5 tests versus the 20 tests that it would be if you compare going across. So it's really based first on your hypothesis, second on the lesser number of evils, in a sense, and so that'll control your type 1 error. Once you pick a direction, though, we're going to split those data sets up to analyze each piece separately, so we'll have to split. This is similar to using split file in SPSS, although not quite as convenient. And I always make myself a little chart here. This is especially useful for doing effect sizes, where I have, for each condition, I have what I'm comparing, so mean 1 to mean 2. So this really forces you to think about the fact that these are pairwise comparisons. And I have their mean, standard deviation, and n. So the way you can get those is use tapply again. So dv first, money. This is where the list function comes in. Okay. So I've got my no out by year and by type. It's not the C function. That would be awesome, but it's not. Okay. So that's where I got those means from. You can copy that twice more. Once for SD to get your standard deviations, and you can see what the problem is that one of them is 112 and some of them are 220, so that's why Levenes' test was significant. And then you can use the length function to get n. So the table function will also work, where you can look at make this table. I just tapply, it's the same thing I've been doing, it's the same pretty output, so I like using the length function. So that's where I got these numbers from. And now I want to compare for each sport by year and figure out those p-values. Okay. This is where I'm going to do a little bit of cutting and pasting. But to create my subset of data sets, I'm going to use the subset function. And so I'm going to create a baseball data set by saying subset my no out data set, where type equal double equals, and then baseball. Okay. If you can't remember what's in the data, oh no, not year, good gracious. There we go. It needs to be spelled exactly the same, and it needs to be double equals, or it will not do anything. Okay. It will create you a data set with all of the lines in it. I have done that before. Don't do it. That creates me a baseball data set. I want to make sure that the number of lines is different, so I'm getting a subset. These are only the baseball transactions. And then I'm going to cheat, so we're not here forever while I'm typing, and create the other 4 data sets. It's the same basic function. I'm just changing this out here. And then all of my little data sets out here should add up to the total number of lines that I was using. After I've created these little mini data sets, what I can do is take this pairwise t-test code. I want to do money as my DV, but year as my IV, and then leave all the rest of this the same. But I don't want that no out data set because that would test my entire data set. I want to change this to do baseball twice. Okay, you can also use the with function. So for baseball, 2007 to 2008, it's 0.025. So that is significant. And then I would run that 5 times. So as you can see, I have it for each of the sports. So let's see. Baseball is significant. What about basketball? Also significant. Football is significant. Soccer, and volleyball. Not too surprising since the main effects were significant. But then I filled in the p-values here, so I know they're all significant. And then I just wrote what that meant. So spending has decreased across years in all of them, which is why there's no interaction. Because their spending is decreasing in all of them. Now that doesn't necessarily preclude an interaction, but I bet you the effect sizes are roughly equal to. So let's see. You can use Mote, which is my free effect size calculator. That's downloadable on my website or our Stats Tools website. But I've also written some effect size code. So the way the effect size code works is I need to open it one. It's not a package, not yet. So I'm going to open F size. Run this entire thing. The computer's running a little slow, so we'll see how long that takes. And this I'm definitely going to copy. But what we're going to do is it's an independent t. So now over here I should have all these extra functions, right? Anytime you want to use this, you will have to run the code again. So I'm going to do const d, an independent t. Okay. And then I would enter all of these numbers. Well, all of these numbers, very conveniently, I showed you the output here, are in my table. So that's why I made this little table. And so I knew what numbers I was using. And so what I want to do is do mean1 equals, I got my 234.76, SD1 equals, you don't have to do these in the same order as me, but it's what I have copied already. Now let's do mean2, so 222.73, SD2, 147.74 into 1483. Now the other pieces of this code that you can manipulate or leave alone is alpha is 0.05. So that just sets the confidence level that you're going to get. K is for the number of decimals. So I'm going to set it to 2 decimals, not 0.02. That'll be very confusing. 2 decimals. So I run this. It's going to give me my means, the standard deviation, standard error of the mean, and their confidence intervals. Also a uncorrected t-test, so I don't want to look at that bad boy. And then here's D. It also gives you the confidence interval of D if you're so interested. You could change alpha to change those confidence intervals. So the first effect size is 0.08. And I would do that 5 times. So I typed all my numbers in. That's probably one of the slowest pieces, is because you do have to manually type these in. So if I look at my effect sizes, trust me, if you run them all, and they're roughly all the same. So there's no interaction because the effect is in the same direction, decreased spending across years, and the effect sizes are all the same. Alright, now I have several videos on ggplot, so I am not going to spend a whole lot of time on it right now. So take my word for it, it works. But you'll load the ggplot package. I have a big block of thematic code that I like to use that kind of cleans up the graph and makes it look manageable. What I want to do is create a bar graph with my current data set. AES, the first piece that you write in is the x-axis. Then what should go on y, and then what the fill is. So how do I pick which one goes in the legend and which one goes on x? I always put the thing you split by on x, so that the legend has the one that you compared, so the bars line up next to each other. If you have no idea how to figure that out, try and make a graph, and then if it's the wrong way, flip it. However, when I make that bar graph, that just makes me a blank plot out here. So I want to take and use this stat summary. Stat summary is going to calculate the averages for each group and put them on my chart. The second stat summary here is going to calculate a confidence interval error bar for me for each mean. My theme code I ran up here. That's going to clean up this graph. It's not going to be this hideous. XLab is my x-axis label. YLab is my y-axis label. And scale field manual here. Let me run this piece first and show you. What that does is it allows me to change. So I changed here x and y. But this out here, legend out here, is kind of ugly. So what scale fill does, the fill here needs to match the fill here. So if you use color here, this needs to be scale color manual. It allows me to change the name. Name is the label on the top. Values are the colors of the graph. You can also change the labels. Labels would be the numbers here. I don't need to change those, but you can. Run my whole plot again. Should get a nice black and gray graph. This is much more publishable, and it shows that we have the same pattern of data for a year across sports, so no interaction, but definitely a difference between sports and a difference in years. Okay. So all that together, and at the very bottom, if you want to download this from online, it walks through the graph a little bit slower for you. The very, very, very bottom of this, I made mine orange or purple just for fun, It has an example write-up of how this might look for APA style anyway, and example publishable graph, and that would be a two-way between subjects ANOVA in R.